So far, we have discussed about the statistical descent method and Newton method and today it's conjugate gradient method. And these are for unconstrained problem so far. And we covered the basic definition of the optimization and the property of say basic matrix and other things. And we covered about the necessary and sufficient optimality condition, and then we moved to the statistical descent method and other things. And in order to help this algorithm, we also covered some kind of inexact, also exact line search. I'm just drawing the map of our courses from now on. And the other thing I'd like to cover was a constraint problem, constraint optimization. Also, in constraint optimization, we have to also discuss about the necessary and sufficient optimality condition. And all the relevant algorithms for this constraint optimization problem. And well, there are numerous other approaches, but what I usually do is method. There you go. The other thing, these are for the what we call nonlinear optimization. And there is also linear, like linear programming and the like. I will briefly cover about linear programming. Also, what if our feasible region is not continuous? Something, and in many cases, the variables are mixed. Some variables are continuous, some variables are discrete, and some variables are not even mathematical. So, for that, I'd like to cover something called GA. Also, and sometimes your variables is even cannot be defined. For that kind of thing, we would like to introduce the fuzzy system as well. And for sometimes your optimization function, I mean the objective function is just a black box. There is no way to take a derivative or evaluate anywhere. Then for those kind of systems, we kind of like introduce ANN, which is acronym for artificial neural network. And that was my original plan, but think of the time given to us. We need almost same amount of time to cover this one, as much as we covered about constraint optimization. So, well, the strategy should be more quick, and we have to cut out some of the part. So, I would like to cut out this part. Originally, it was included in the process, and I'm not sure about this response surface method. If we have enough time, we will cover that. And this is GA and RSM is quite useful because in industry we have plenty of the computer power, but the problem is really complex and cannot be easily modeled into the constrained or unconstrained problem. Okay? And I'm not sure about this linear programming as well. Anyway, from now on, I will just briefly cover what's that. But for that part, necessary and sufficient optimality condition, we still have to do some kind of mathematical proof. It's a really important concept. Okay. Yeah, I said the time management. Anyway, the important thing is you got to know the inner mechanism of constraint optimization. Unconstrained optimization with these nice conditions. First of all, what I really want you to understand is you got to know the problem itself, the property of the problem. I mean, the solution exists or is solution unique. You got to know if it is possible. Because running this optimization algorithm in most of the cases very time consuming and computationally very expensive. You have to take advantage of what's already given. If you know the problem characteristic, you can just run the most required thing, not without any redundant work. So, for that whole, I covered some mathematical definition, and based on that, for example, the three method. For example, function is continuous, differentiable, and what if the objective function is convex? Then you can say that these algorithms are guaranteed to find the global optimum. Okay. How do you identify the problem itself is convex? Well, based on the quadratic form and other things, you can identify this is convex problem or not, or something like that. If that's the case, most simple cases, continuous, differentiable, twice differentiable, and convex, then you can easily solve this kind of optimization problem. Okay. Steepest descent method, just very straightforward method. You're just following the slope. Let's say you're on some map of mountains and valleys. If you pour some water and assume that this water is not absorbed by the soil, if you follow that water, then you will end up in the lowest point. That's the point of steepest descent method. In order to do that, you have to know some kind of line search method. Whatever goes golden section, line search, or bisection, whatever line search method, as long as it's effective, you can use it. You can mix and match and whatever you want. For the Newton method, this one utilizes the second derivative, I mean the curvature of the Hessian. For that, it is more faster usually in use most of the time because it knows another information. However, sometimes it is not that easy to calculate the Hessian. No. Okay. But anyway, the method is exactly the same. It follows the steepest descent direction, which is one of the descent direction, which is minus the gradient. Newton method is following Newton direction, which is minus gradient and Hessian. So, but this one is rather slower than Newton method, but this one requires a very complex Hessian calculation. Conjugate gradient method are developed by these two ends. They want to mix and they want to have the middle of the performance. Okay, so that's the conjugate gradient method. Well, there is a lot of method to solve the unconstrained optimization. If you refer to one of the reference book I listed in the beginning of the classes, well, you will have about 10 or 20s of the algorithm. They have their own strong point and weak point, but the basic concept is very similar. Okay. All methods are doing all methods define their own descent method. The only difference is their definition of the descent method based on the other situations as well. This one, conjugate gradient method, is also another descent method, and their definition of descent direction is a little bit different. Okay. First one is we have to define conjugate. Suppose Q is positive, infinite, and symmetric matrix, and the vector B1, B2, Bk are called Q conjugate. If it's not zero, and B transpose I, EI transpose Q EI, sorry, EJ is 0 for that's the definition of the conjugate. Well, the terminology conjugate is not new. I think we already know about the conjugate of imaginary numbers. So I plus EI, if that's the imaginary number, the conjugate imaginary number is n minus EI. The concept is exactly the same, but now these are defined conjugate vectors for symmetric or symmetric matrix. That's the conjugate. Okay. Let me ask you a question. Since Q is positive definite, if we take the same vector which is non-zero, then this one should not be zero, right? That's the definition of positive definite. It should be greater than zero, right? But in this definition, the vectors are different. If for different EI and EJ, if you take this form, it should be 0, 2, and based on this one, we can conjecture that such kind of position is, I mean, if you're familiar with this linear algebra, do you know what's the dependent and linearly dependent and linearly independent vector? Okay. Anyway. Linearly dependent vectors are basically, if you have three vectors A, B, C, and if these are linearly dependent, then you can make C out of some in this form. If these A, B, C are linearly dependent. If it's not linearly dependent, I mean linearly independent, then there is no way to make this equation. For example, simple one is if you have vector 1, 0, 0, and 0, 1, 0, 0, 0, 1. So just transpose sign. Are these linearly dependent or independent? Independent. Right? That's why we are using this as the basis of our three-dimensional space. You need at least 3. Okay? Okay. And we call this linearly independent and unique vectors are basis of some space or something like that. Okay, now we have another linearly independent vectors, D1, D2, D3, until Dk. What does this do in our visualization? Okay, let's look into a little bit into this. Okay, by proving this one. Suppose that these are linearly dependent. lambda 2 lambda k, it is possible to find out, it is possible to satisfy this one if we choose lambda 1, lambda 2, lambda 3, and lambda k properly. So, first of all, I'm just nullifying the statement. What if this is linearly dependent? Then it should satisfy this. Okay? Then what you're going to do is multiplying this Ej transpose Q in front of all these statements, equations. Number 1, E1, 2, E2, K. Since we are multiplying something to 0, it should equal to 0. Right here, and this one is, if you evaluate it, it's nothing more than Ej transpose Q from the 1 to 1, from the 2, Ej transpose Q from the K, Ej transpose Q, K. Right? Because lambda is a scalar. And we know that if these J and N like this, if I and J is not equal to each other, then it is 0. Because DI's are defined in such a way. So 0 if J is not equal to 1. 0, 0, 0, and what's left is lambda J, Ej, transpose Q, Ej. Right? Nothing other than this term will be 0. But the remaining term is also 0. But we know that since Q is positive definite, this should be greater than 0, which means lambda J should be 0. From this, we can say that all lambda J is equal to 0. Why? Because if we take lambda J is 1, then lambda from this one we can say that lambda 1 is 0. If we take lambda, is it convenient to follow this one? We can put any J out of 1 to K, right? So for all J, this all lambda J is equal to 0, right? If we take J is 1, and we know lambda 1 is 0. If we put J is number 2, lambda 2 is 0. For all J, this is true. Which means this is contradiction. So this conjugate should be linearly independent to each other. Question? Okay. let's say there is a objective function in quadratic form. Okay, X is a vector, Q is a matrix, large Q is a matrix, small q is also vector. This is a simple quadratic form. And let's assume this Q is symmetric and convoluted. And suppose that we want to minimize it. And we need to minimize it. Okay. And recall that what's the gradient of fx? So scalar function derivation with respect to a vector, right? But anyway, the concept is exactly the same. First one, next one, so it's anyway, this is qx. That's the gradient. And suppose that we are given the direction p1, p2, pn that are q conjugate. And suppose that we already given a starting point. And based on all this, we can apply this direction. The next point is from the starting point to the following this on the J. So we can follow this direction, right? And let's assume that what will happen if we follow this direction. So x is equal to from starting point to right. And please keep in mind we are only evaluating with respect to this quadratic form. If you do the evaluation, you will end up in here. Q transpose x1 plus lambda j Q transpose ej plus f of b x1 and Q simple, right? You just plug this x1 plus summation lambda j dj into this function. And if you do the evaluation once more, it is x1 plus, since we know this is the gradient form, any question from this step to that step? We are just utilizing the gradient form. Okay, evaluating this and plug that form into the gradient form, we will end up in this form, and which is exactly the same as just another form. Okay, and keep that in mind. Since we are optimizing in n-dimensional space, we have j from 1 to n, because Q is symmetric and positively infinite matrix in n-dimensional space. So there is another way to summarize, evaluate. For example, we gather all lambda first and rest of it. And go back to the here. It's a B generic form of the quadratic problem. And we suppose that x1 is the starting point, and we move follow this direction because DJs are linearly independent direction, and summation of it makes some dimension direction, right? For example, like these are three linearly independent unit vector, x, y, z vector, and by doing this form of thing, we can make a arbitrary direction in this three-dimensional space, right? Same thing here. Given n-dimensional space, if you take this linearly independent direction in this summation form, we can make a arbitrary direction, and this x-axis, we are moving from 1 to x, following that direction, and we evaluate it, and we'd like to minimize it, right? And we'd like to minimize it, because we minimize this one, then that means we are following some direction which minimizes our effect. So okay, for each lambda j's, it is proven that if we follow this lambda, if we select this lambda j like this, as I mentioned before, dj's are given. dj's are the direction is given. But by changing this lambda j's, we can arbitrarily make the direction. And if we choose this lambda j tilde, which minimizes that part. Okay. So let's say this is x star, which is a minimized point. Okay. And this is conjugate gradient direction. Okay, thing is like that. This conjugate gradient, conjugate direction is something like this. This is a function. My statement from now on is not mathematically correct, but I'm just giving the concept. This fx is a n-dimensional function, mapping n-dimensional x into one-dimensional x. It should return a scalar value, right? This is a mapping, an n-dimensional mapping, n to one-dimensional mapping, and if it has this kind of quadratic form with every symmetric positive semi-definite one, there is linearly independent conjugate direction. Okay, so if we change your mind from this physical space into the function space, then you are in the n-dimensional space. And the basis vector of this function space is this Q conjugate. Okay? And without losing your way or doing non-necessary steps, you are following the very best direction inside of your function space. And that's the conjugate direction. And this conjugate gradient method defines the descent direction based on this function's conjugate direction. And it is known that it's a middle of this steepest descent method and Newton method. You know, Newton method has fast convergence ratio, but it is computationally expensive since it calculates the Hessian. Well, the steepest descent method is not that fast. It is just going step by step. However, you only have to evaluate the one gradient. This conjugate gradient method is kind of mixing these two. It does not evaluate any Hessian, right? No Hessian. It only requires gradient. However, this direction is much better than this only the steepest descent direction. So it's a little bit faster than the steepest descent direction. However, it requires a little more calculation. Not that much of Hessian, but it requires a little more calculation to find this direction. That's the conjugate gradient method. Question? Okay, you guys are supposed to do the MATLAB, a very little MATLAB tutoring in this previous homework, and I think you already noticed that there is a toolbox in MATLAB, right? And there is an optimization toolbox, right? And inside of this optimization toolbox, steep descent, Newton, conjugate gradient, and secant, and all the algorithms are already there. You are just grab the relevant function out of this toolbox and run the program. Okay. But the important thing is you should know what you're doing. Without knowing what you're doing, then cannot deliver your results, right? That's why we are still learning the structural mechanics, even though there are Nastran and ANSYS and Abacus out there, right? You got to know something to use those kind of software. Same thing here. Okay. Conjugate gradient algorithm. We suppose that we already know the conjugate directions. Then, let's say x1 is starting point, and this E1 to EK are Q conjugate. And we assume that we already know these two. And the algorithm for this conjugate gradient is very simple. Step K. Okay. Given K, we compute the minimum of the following function. For the corrected function, and this is exactly same as Would you like to solve this one? So, and we know that if we follow this lambda, okay, and xk plus 1 That's just our we are assumed that we already know conjugate direction of Q. Let me ask you a question. Let's say this is the minimum, and this is our starting point x1. And it's x and y. And this function value is on g direction. It's just three-dimensional space surfaces. Okay. As I mentioned before, this is following the basis direction in the functional space. And for this function, it's a two-dimensional. I mean, x is, because it's an x and y space. And the function itself is mapping on, right? Okay. Having said that, how many steps are required to reach the optimum using conjugate gradient method? Two, only two. The concept of iteration is a little bit different here. You're just following one conjugate direction. I don't know, maybe this direction or that direction. But as long as this has the two conjugate direction, E1 and E2, if you follow that one step by step, then you're there. Okay? It's like this. Assume this is two-dimensional spaces, and these spaces are the conjugate, Q conjugate. And since we are dealing with the functional space, not the physical space, what you're doing is, using that algorithm, is you find the lowest optimum in first direction. And once you set, and the lowest in this direction. That's good. So that's the concept of the conjugate gradient algorithm. For this algorithm, we mentioned that we already know the conjugate direction, but in most of cases, we don't know about this conjugate direction. So The next step is to expand our problem into more generic concepts, like just conjugate graded algorithm without knowing conjugate ratio. Okay. Here, a quadratic function, and this Q is symmetric, positive. So far, we assume that we have already known the available Q conjugate E1 to En. In this section, from now on, we assume that we don't know about this Q conjugate yet. And we have to generate a set of N Q conjugate. And I'd like to add this on the slide, which means in every iteration we have to calculate that conjugate direction. Not pre-calculate all possible conjugate direction, but have to do on the fly on every iteration. One direction at a time. Okay, starting point is very simple. That x1 is a starting point, and let the first direction E1. I would like to mention one more thing. In 3D space, there is no single way to set the basis. As long as they are orthogonal, then we can set any basis function. Same thing here. For the first direction, we can choose any direction. Okay, so the natural choice of the first thing is equals to the descent direction. Okay? And based on that, we can calculate the D2, D3, D4, something like that. Since we define D1, and based on that, we can calculate D2, and we can calculate the D3 with D1 and D2, and something like that. For example, in 3D space, we arbitrarily set this is X, and then we can also arbitrarily set Y, which is perpendicular or linearly independent. And based on these two, we can set Z. The concept is same here. Okay? So, let's say this is first equation. And this is what you're going to do. Oh, sorry, what we are going to do here. And we already know that this lambda at k is equal to minus right? dk plus 1 is defined as with alpha k is okay. This form is very similar to this steepest descent algorithm, but now it is about this direction, and you can say that this is, for example, if this is your steepest descent direction at this point, and let's say this is your dk direction, you follow this dk direction to reach here, since this is xk. And using this one is this is dk direction here. So you're mixing this steepest descent direction with your previous conjugate direction to make a new conjugate direction. Okay? And at this point, since this calculation of conjugate direction is done by sequentially, you have to know D1 and D2 to calculate the D3. So at this point, only the dk plus 1 and dk are conjugate direction. And based on these two, you have to calculate another conjugate direction. Okay. And to prove it, we need lots of proof and theorem once again. So I will skip the proof and I will just read the algorithm. There's the algorithm. The step 1 do loop will end here. So this is do loop. Okay, and this right about this alpha k is a little different. What we talked about before. For this one, I just write a more general term. So this will we hold also non-quadratic function as well. It's a generic one. So this is the conjugate gradient method, conjugate gradient algorithm for non-quadratic function. Okay. Anyway, as long as you capture the concept, then okay. Let's close today's lecture here, and from this Wednesday we will continue to the constraint optimization. And for the constraint optimization, the basic concepts are already covered. You only have to consider the differences of this boundary and the constraint. So it will be more quick. And homework number 6 will be distributed soon. It's about MATLAB coding, applies all this. Okay. Thank you.